Hello, welcome to this video. So, we all know the infamous formula by Euler that says e to the ix is equal to cosine x plus I sine x, where I is the imaginary number that satisfies I squared is equal to -1. But, what if I is not the only one out there? What if there are more imaginary or even complex numbers that satisfy this property? So, today what we're going to do is look at e to the zx is equal to cosine x plus z sine x, z sine x, where z is a complex number. So it could be that z is something like 2 or 5, or maybe it's negative 3i or 5 plus 10i. It's a complex number. And this is true for all x. And we want to find all complex numbers that satisfy this. Now, you might at first think that we will separate z into a plus bi, and then we will use this formula in order to try to get some things, try to get some equations for z. For a and b, they'll maybe get us to find what z is. But I tried it and it doesn't seem to lead anywhere. Maybe you tried, maybe you can solve it this way, but I couldn't. But I couldn't when I first tried. Instead, we're gonna look at how this formula was proven to be true. The way it was shown was with the Taylor series of each one of those terms. You looked at the Taylor series of e to the ix, and then cosine x, and then sine x, and then you can see just that the Taylor series of e to the ix is simply cosine x plus sine x, but sine x is times I. So e to the ix is cosine x plus I sine x. And we use the Taylor series, which I did a whole nother video about. I'll link it in the description. But the Taylor series basically allows us to take a function. It's not every function. There are some functions that can be represented this way, but there are functions that, if I'm not mistaken, are called analytic. They can't be represented this way. And by this way, I mean as a polynomial. Maybe an infinite one, but still a polynomial. So for example, e to the x is analytic, and it is represented as 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And and cosine and sine are also analytic, so we can also find Taylor series for both of them. And this question will be much easier to tackle if both sides would be polynomials, with z just as part of the coefficients. Because then, if we know that two polynomials are equal, we know that the coefficients of each power of x will be the same, and then we will be able to solve for z. So let's begin. So first of all, I'm gonna write. I already wrote the Taylor series for e to the x. I'm gonna write the one for cosine and sine, so it's easier to get the Taylor series of this and of this. So cosine x is equal to 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, and so on. And sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial, and so on. So the ones for cosine and sine are sort of like taking a part of each the x, maybe the even ones and the odd ones, and then put alternating signs on it. So cosine, it takes all the evens and then puts alternating signs. Sine takes all the odds and puts alternating signs. Okay, now all we need to do is simply substitute all of these into these equations, and then we will know that the coefficients of x to the power of something here will be the same as x to the power of that same number over here. Okay, so e to the zx. That's just simply replacing x here with z. So we're gonna have e to the zx equal to 1 plus zx plus zx squared over 2 factorial plus zx cubed over 3 factorial, and so on. All we're doing is substituting z times x into here. Okay, now cosine x. We already have this written out. I'll write it again here just so we have a nice order here. Okay, and now to, z sine x, it will simply be this times z. Nothing revolutionary going on here. Okay. Now we have this. Now we know that we want this plus this to equal this. So we'll just look at the coefficients. So first of all, let's look at the even ones. And we're going to separately do the even ones and the odd ones. Because cosine x only has the even ones, only even powers, and sine x only has odd powers. So if we look at them separately, we will know that the even coefficients and the coefficients of the even powers in e to the zx will be the same in cosine x, and similarly for z times sine x with the odd powers. So for even ones, we'll be able to say that the coefficient of each number here is coefficient of the nth power of x to the n is we're dividing by n factorial, but remember we replaced x with z times x, and raised to the power of n, that is z to the n times x to the n, meaning that we need to multiply these coefficients by z to the n. But because we're looking at even numbers, we will replace n with 2n. So all we need to do is something like this. And now, the 2nth, now the 2nth coefficients here is the same as the nth coefficients here, because the power in each one will be x to the 2n. And here, the coefficients of x to the 2n, you can see it's negative 1 to the n over 2n factorial. So again, you can see we're dividing by the factorial of each power. So that's why we're dividing by this 2n factorial here. And we're alternating the signs. So this is why this negative 1 to the n is here. Now we can multiply by 2n factorial to get z to the 2n is equal to negative 1 to the n. If this is equal to all n, then we can safely say that z to the power of 2 is negative 1 by essentially doing the nth root. Because we know this is true for all n, now z squared is equal to negative 1, meaning that z is equal to plus or minus I. Meaning that z is equal to plus or minus I. Now, this doesn't solve everything. This is only the even powers. We still need to do the odd powers for z sine x. But as you'll see, we'll get the exact same thing, that z is equal to plus minus I. But we'll still do it. Okay, so we found out that when we're looking at even powers and getting the coefficients to equal, we get that that z is equal to plus or minus I. But now we need to look at the odd powers. So, like we saw before, the coefficients of the nth power in e to the zx is z to the n over n factorial. But now because we're looking at odd powers, I'm going to put 2n plus 1 instead of n. So z to the 2n plus 1 divided by 2n plus 1 factorial. And now, this is the coefficients of x to the 2n plus 1. And now, the coefficients of z sine x of x in z sine x of x to the 2n plus 1. First of all, you can see we're multiplying by z, so we have z. Then we're dividing by the factorial of the power again. So this is divided by 2n plus 1 factorial. But again, we have alternating signs. So this is times negative 1 to the n, which takes care of the alternating signs. Now, we know these are equal. And then again, we can cancel out the 2n plus 1 factorial. And we also know that z cannot be 0 because we found out that if z is a solution, it has to be plus or minus I. So we can also divide by z, and we'll get negative 1 to the n. And negative 1 to the n is equal to z to the 2n. Again, because this is true for all n, we get that z squared is equal to negative 1. And once again, z is equal to plus minus I. So in both cases of the coefficients of the even powers and the coefficients of the odd powers, in both of them we got the result that z is equal to plus or minus I. So this should be our solution, right? Well, not so fast. We have to check if these are solutions. So we already know by Euler's formula the z is equal to plus I is a solution. Z is equal to negative I is also a solution, because if we look at e to the negative ix, we can look at this as e to the I times negative x. And then we can use this formula that we know is true to get that this is cosine negative x plus I sine negative x. Cosine of negative x is cosine of x. Sine of negative x is negative sine of x. This is an even function, this is a non-function. So this is cosine x minus I sine x. And the property still holds. We have cosine x plus this number that we're multiplied by x here times sine x. So negative I also holds. So we got that not only are these two that these two satisfy this property. They're the only complex numbers that satisfy this property. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it.